Picture this: the fabric of our universe and everything in it is composed of tiny entities known as atoms. These atoms are the fundamental units from which everything around us is made. But how did these atoms come into existence? What's their origin? Despite their minuscule size, could atoms collectively resemble a colossal cosmic atom? Imagine an atom as a small core known as a nucleus, surrounded by electrons whirling around it at incredible speeds. But how do these electrons maintain their perpetual motion around the nucleus? This question sparked significant curiosity in the early 20th century, paving the way for the emergence of quantum mechanics, a captivating field of study. Scientists were determined to unravel the mysteries surrounding atoms. They discovered that each atom has a nucleus, which serves as a central hub with a positive charge and significant mass. Surrounding this nucleus are extremely tiny electrons carrying a negative charge. Armed with this basic understanding, scientists began crafting a more intricate model of the atom. Initially, scientists thought of atoms as miniature solar systems, with a central nucleus resembling the Sun and smaller particles orbiting around it like planets. However, this model faced two major challenges. First, as charged particles move, they emit electromagnetic radiation. According to this model, electrons, being charged and in motion around the nucleus, should continually emit radiation, leading to energy loss and an eventual collision with the nucleus. Yet, atoms last far longer than just a fraction of a second, making this model unfeasible. Secondly, atoms were observed emitting radiation at specific frequencies, unlike the continuous emission expected if electrons behaved like planets in the solar system. Let's talk about Niels Bohr, a revered physicist from Denmark who tackled these challenges head-on. In 1913, he introduced a groundbreaking idea: electrons within an atom do not move erratically. Instead, they are confined to specific, fixed distances from the nucleus. Bohr took it a step further by proposing a minimum distance that an electron could maintain from the nucleus, beyond which it could not approach any closer. Bohr's revolutionary ideas were not mere conjectures, they were based on the pioneering work of Max Planck, a German physicist who had made significant strides in understanding radiation about a decade earlier. Planck's key insight was that when objects emit or absorb radiation, they do so in discrete, fixed amounts rather than in arbitrary quantities. These fixed amounts were governed by a constant value known as Planck's constant. Building on Planck's concepts, Bohr extended them to the movement of electrons around a nucleus. He proposed that the smallest orbit an electron could occupy would have a specific amount of angular momentum, precisely equal to Planck's constant. Larger orbits could contain multiples of this constant, such as 2 or 3 times its value, but they couldn't exist in fractional amounts like 1.3 or 2.6. Bohr's detailed model laid the foundation for a deeper understanding of atomic structure, unlocking insights into how electrons behave within atoms. However, fully understanding why electrons follow specific paths and adhere to particular energy levels required further development of quantum mechanics. Electrons, like other subatomic particles, exhibit both particle-like and wave-like behaviors. While we might envision an electron as a tiny planet orbiting a nucleus, it can also be conceptualized as a wave enveloping the nucleus. When confined within a limited space, waves adhere to specific rules. They cannot possess arbitrary wavelengths but must conform to patterns dictated by the space they occupy. An analogy to playing a guitar illustrates this concept. Only certain lengths of a string produce distinct notes when pressed down, just as the electron wave encircling a nucleus must conform to the available space, with the closest orbit corresponding to the first pattern of that electron's wave. As scientists delved deeper into quantum mechanics, they refined the model, yet the fundamental idea persisted: an electron's proximity to the nucleus is constrained by its quantum limitations, which prevent it from occupying a smaller space. This analogy, likening electron behavior to musical harmonics, facilitates an understanding of the intriguing link between quantum mechanics and the movement of particles on a minuscule scale. Another perspective on this phenomenon doesn't involve delving into the complexities of quantum mechanics. Instead, it focuses on the interplay of various energies. Picture an electron orbiting a nucleus. It experiences a pull toward the nucleus due to electric forces, constantly attempting to draw nearer. Simultaneously, it possesses kinetic energy that pushes it away. For an atom to remain stable, these opposing forces must balance each other out. The total energy of the electron in its orbit, comprising both its kinetic and potential energies, is negative. Therefore, to remove the electron from the atom, energy must be added to the system. This situation bears resemblance to planets orbiting the Sun. Extra energy is required to dislodge a planet from the solar system. Imagine an electron being drawn toward the nucleus due to its electric charge. However, because of the constraints imposed by quantum mechanics, it cannot quite reach the nucleus and thus remains in orbit. This phenomenon is permissible in physics because the overall energy of the system is negative, indicating stability in maintaining cohesion to form a durable atom. Now, let's embark on a captivating journey to understand the genesis of the first atom, a journey deeply intertwined with the vast expanse of our universe. Everything around us, from the tiniest particles to the grandest stars, is composed of an astonishing multitude of atoms, surpassing comprehension in the observable universe. These atoms, the fundamental constituents of matter, consist of even smaller entities, electrons, protons, and neutrons, which in turn are composed of minuscule components called quarks. The narrative of these particles begins with a monumental event known as the Big Bang. The Big Bang theory offers insights into the origin of the universe, proposing that an immense amount of energy condensed at the universe's inception, leading to the formation of atoms. However, this account merely scratches the surface of our cosmic exploration, as comprehending the Big Bang in detail necessitates delving into the events of the early universe. Regrettably, the exact moment of the universe's inception remains elusive, leaving us pondering whether it truly had a definitive beginning. The Standard Model of Cosmology, our most reliable framework for understanding the universe's history, enables us to trace time back to a juncture near the universe's origin. According to this theory, a singularity, a moment of infinite density, marked the inception where all matter and energy were compressed into an inconceivably tiny space. Nonetheless, some physicists cast doubt on the accuracy of this prediction. Our scientific expedition ventures back to a time incredibly close to the universe's birth, approximately 1 Planck time, about 10 to the power of minus 43 seconds. However, once we approach this juncture, our comprehension falters. Before this infinitesimal fraction of time elapses, the universe's earliest moments remain shrouded in mystery, beyond our observational reach. In our quest for knowledge, we edge ever closer to the moment of time's genesis, yet the precise instant when time equals 1 remains an enigmatic puzzle, compelling us to delve deeper. To delve into the universe's primal epoch, we must explore a theory melding two fundamental principles, gravity and quantum mechanics. This theory, known as quantum gravity, elucidates the behaviors of celestial bodies like stars and planets as well as the interactions of subatomic particles. Our cosmic odyssey transports us to a phase termed the Planck epoch, occurring at a staggeringly brief interval of 10 to the power of minus 43 seconds. During this epoch, it's conjectured that all fundamental forces, such as electromagnetism, the weak force, the strong force, and gravity, coalesced into a singular unified force. Let's embark on a systematic journey through the Big Bang theory, commencing prior to the Planck epoch, which signifies the inception of cosmic evolution. However, before we plunge into this epoch, caution is warranted. The state of the universe during this primordial era and the events preceding it remain uncertain due to the singularity at t equals 1, the moment of time's inception. Our expedition commences with a phase known as inflation, occurring shortly after the Big Bang, spanning from about 10 to the power of minus 36 seconds to approximately 10 to the power of minus 33 seconds. During inflation, the universe underwent an extraordinary period of expansion, surpassing human comprehension. This expansion occurred at such a rapid pace that it transformed the universe from a minute point to a size akin to that of a large orange. It's imperative to grasp that while information cannot exceed the speed of light, inflation entails the expansion of space itself. Consequently, remote regions in the universe can drift apart at velocities surpassing the speed of light. While the inflationary period offers glimpses into the universe's infancy, our most concrete understanding stems from the post-inflationary point in space and time. But a phase when the universe was intensely hot, dense, and rapidly expanding. As we navigate this cosmic chronology, we unravel the mysteries surrounding the universe's genesis and contemplate the formidable forces shaping its evolution. Inflation is presumed to have occurred between approximately 10 to the power of minus 36 and 10 to the power of minus 33 seconds after the Big Bang. The impetus driving this expansion remains unidentified, and inflation obliterates any traces of what transpired prior. The Standard Model of cosmology adeptly elucidates events from roughly 10 to the power of minus 12 seconds after the Big Bang, as modern-day particle accelerators can replicate the universe's energy levels before this juncture. Conjectures abound regarding the period spanning from about 10 to the power of minus 33 seconds to 10 to the power of minus 2 seconds, during which gravity, the strong force, and the electromagnetic and weak forces were unified. The origins of the first elementary particles, those without mass, present a cosmic conundrum with various possible explanations. One notion proposes that they originated amidst the intense energy of the Big Bang, while another theory suggests their emergence stemmed from a metamorphosis within an inflation field. This transformation converted inflaton particles into the elementary particles constituting the universe today. This cosmic narrative unfolds around 10 to the power of minus 11 seconds after the Big Bang, initiating the quark epoch as temperatures plummet to about 10 to the power of 15 Kelvin. During this epoch, the universe witnesses a dynamic interplay between electromagnetism and the weak force, culminating in a phenomenon known as electroweak symmetry breaking. Concurrently, the Higgs field acquires a non-zero potential, imparting mass to the elementary particles delineated by the Standard Model of particle physics. This lays the groundwork for the eventual formation of atoms as the early universe's temperature skyrockets to an astonishing 1 quadrillion Kelvin. As the universe continues to expand and cool, the exceedingly high temperatures hinder quarks from coalescing into composite particles like protons and neutrons. However, around 10 to the power of minus 5 seconds after the Big Bang, as the temperature dips to approximately 1 trillion Kelvin, a remarkable transformation occurs. The quark plasma metamorphoses into a composite mixture of particles known as a hadron gas, comprising protons, neutrons, and specific varieties of mesons. Subsequently, these mesons undergo further transformations, giving rise to the emergence of photons and electrons. With each reduction in temperature, particles and their antimatter counterparts annihilate each other. Nonetheless, due to a slight imbalance in this process, certain particles, such as specific types of quarks and electrons, persist. This remnant matter proves pivotal for the formation of protons, neutrons, and electrons, the fundamental constituents necessary for crafting the earliest atoms. This intricate choreography of particles and forces shapes the narrative of the universe, laying the foundation for its evolutionary trajectory. Approximately 1 second after the Big Bang, during a phase dubbed the lepton epoch, temperatures plummet to around 5 billion Kelvin. It's at this juncture that particles known as leptons complete their annihilation process. Following this event, the majority of matter particles transform into photons and neutrinos. However, due to the disparity between matter and antimatter, a small residue of protons, neutrons, and electrons endures. These residual particles serve as the fundamental constituents for the formation of atoms. A short while after the universe's inception, a pivotal phase called Big Bang nucleosynthesis commences. During this period, an equal number of protons and neutrons are generated. Neutrons, however, are inherently unstable and undergo beta decay, transforming into protons within approximately 10 to the power of minus 5 minutes. While temperatures remain elevated, the conversion between protons and neutrons remains balanced. However, as the universe gradually cools, more neutrons decay. Some of these neutrons combine with other particles, forming larger nuclei before disintegrating. Consequently, the universe predominantly comprises hydrogen nuclei interspersed with helium, 4 nuclei and trace amounts of other elements like deuterium, helium-3, and minute quantities of lithium nuclei. And the cosmic narrative, a pivotal segment unfolds known as the photon epoch, spanning roughly 380,000 years. Throughout this period, the universe is predominantly filled with ionized nuclei devoid of orbiting electrons. For stable, neutral atoms to form, electrons must interact with these positively charged nuclei. However, due to the universe's elevated temperature, electrons and nuclei struggle to remain bound before electrons gain excessive energy and break free. This perpetual disengagement creates a hazy environment where photons, carriers of light, incessantly collide with nuclei and electrons, impeding their progress through space. This phase endures until the universe cools to approximately 3000 Kelvin. At this juncture, electrons, now possessing diminished energy, are captured by the electromagnetic force, forming stable bonds with nuclei in a process known as recombination. This marks the emergence of stable, neutral atoms, liberating photons from their prior entanglement with the swirling amalgamation of positively charged nuclei and negatively charged electrons. Subsequently, these photons traverse space unhindered. For denizens of the universe, this journey of light unfolds as a mesmerizing spectacle. Presently, we can observe the cosmic microwave background radiation emanating from all directions. This luminous radiation captures the moment when the first stable, neutral atoms materialize, furnishing invaluable insights into the early universe and the genesis of atoms. As we contemplate the enigmas of the cosmos, a thought-provoking question arises: do atoms ever truly make contact with one another? This inquiry beckons us to explore the fundamental nature of atomic interactions, prompting reflection on the profound mysteries governing the behavior of these elemental constituents in the cosmos. Atomic interactions are incessant, yet comprehending these exchanges demands a reconsideration of the concept of interaction. In our everyday encounters, interactions are typically observable or tangible. For instance, when two magnets are brought close together, their interaction is visible, or when two charged balloons approach each other, the force between them is palpable. In these scenarios, the properties of the magnet's poles or the charge on the balloons dictate their interaction, facilitating a dynamic exchange on a scale perceptible to us. However, when we scrutinize interactions at the atomic level, the complexity amplifies. At this scale, atoms and molecules are in perpetual motion, colliding and spinning in a chaotic ballet. We discern that atoms lack a distinct boundary as we might anticipate. Instead, electrons exist within a probability cloud, delineating their potential locations. Quantum mechanics elucidates these probabilities, unveiling their extension throughout the cosmos. Although electrons typically remain in close proximity to the nucleus in most observable situations, the absence of a tangible surface implies that atoms do not physically make contact in the manner akin to our everyday tactile experiences. Nonetheless, there persists a profound and influential interaction between them. Atoms are in a constant state of interaction primarily due to the electromagnetic force generated by the electric charges of electrons and protons within them. While this force technically extends infinitely, its impact becomes significant only when atoms are in close proximity. At times, atoms repel each other because of the electromagnetic force between their electrons. During such instances, describing their interaction as anything other than touching can be challenging despite the absence of immediate contact. Nevertheless, it's still regarded as a form of contact. Consider a cup resting on a table. At the atomic level, even though there's space between them, the electrons on the cup's outer edge repel those on the table's outer edge, signifying a significant interaction. This is evident from the cup's stability on the table. The electromagnetic forces between the atoms counteract gravity's pull. On a broader scale, when we say two objects are touching, it reflects a similar interaction transpiring at the microscopic level. Atom interactions can vary, and they're not solely about being repelled by electromagnetic forces. When atoms draw close to each other, another force known as the van der Waals force, a component of the electromagnetic force, can foster bonds between them, leading to the creation of molecules. In a molecule, atoms are essentially in contact with each other. Intriguingly, even the nuclei within atoms can potentially come into contact, albeit challenging due to the strong electromagnetic repulsion between positively charged protons in each nucleus. Here, quantum mechanics comes into play. If two atoms are brought together and held in place for a duration, there's a random possibility that their nuclei can fuse. This process, termed nuclear fusion, entails two distinct atoms merging into a single larger atom. When the involved atoms are lighter than iron, this fusion releases energy. This fundamental mechanism is how stars, including our Sun, generate the energy that sustains their luminosity. Let's delve into the concept of identical atoms within the same element. Contrary to intuition, two atoms of the same chemical element aren't always identical. This discrepancy arises because electrons within an atom can exist in different energy states. Thus, if two atoms of the same element have electrons in varying states, they can differ from each other. For instance, envision one copper atom with an excited electron and another with all electrons in their lowest energy state. These two atoms exhibit disparity. The excited copper atom emits light when the electron returns to its lowest energy state, whereas the other doesn't. How an atom chemically bonds with other atoms hinges on the energy states of its electrons. Consequently, two atoms of the same element may react dissimilarly if their electrons are in different states. Chemists recognize the critical role of understanding in specifying the energy states of electrons within atoms to fully grasp and forecast reactions. Even when atoms of the same element possess electrons in identical energy states, they are not truly identical due to factors such as differing movement or rotation speeds, which impact their ability to form chemical bonds. Atoms with slower movement, such as those in solid form, have sufficient time to form stable bonds, while faster-moving atoms, like those in liquid form, struggle to do so. Consequently, a tin atom moving slowly behaves differently from one moving quickly. Consider a scenario where two atoms of the same element possess electrons in the same energy states and move and spin at identical speeds. Would they be identical? The answer is no. Similar to electrons, neutrons and protons within an atom's nucleus can also exist in different energy states. Furthermore, the nucleus as a whole can undergo rotation and vibration at varying speeds. Thus, even with all other factors held constant, two atoms of gold might have nuclei in different energy states, leading to disparate behaviors in nuclear reactions. Achieving perfect identicalness between two atoms of the same kind is exceedingly challenging. Despite two atoms being chemically indistinguishable and reacting similarly, they cannot be deemed entirely identical. This principle extends beyond electrons to encompass the nucleus of an atom, comprised of tightly bound neutrons and protons. It's vital to grasp that atoms of the same type may possess different neutron numbers yet remain the same atomic species. These differences are termed isotopes, carrying significant implications, particularly in nuclear reactions like radioactive decay. While the presence of a specific isotope does not impact an atom's chemical reactions, it profoundly influences its behavior in nuclear reactions. Varied isotopes decay at distinct rates and exhibit unique characteristics during radioactive processes. Some isotopes decay rapidly, transforming into other elements while emitting radiation, whereas others remain stable. In scenarios such as carbon dating, discerning between isotopes of the same element is crucial. For instance, a carbon-12 atom differs from a carbon-14 atom. Simply tallying the total carbon atoms in a sample does not reveal its age. Instead, analyzing the presence of different carbon isotopes within the sample is imperative. It's important to acknowledge that atoms lack unique identities beyond the characteristics we've already discussed. If two carbon atoms exist in precisely the same molecular, atomic, electronic, and nuclear states, they are indistinguishable regardless of their origin or past experiences. As the fundamental constituents of matter, do atoms possess colors? This question prompts further inquiry. When numerous atoms aggregate, as in the composition of the screen you're viewing, color becomes apparent. But does each individual atom harbor its distinct hue? If so, is it the nucleus or the electrons that exhibit color, and if color exists at this scale, what would it entail? The colors we perceive are constructs of our brains, they do not exist independently of our visual interpretation. To comprehend this, we must delve into the nature of light. Light comprises particles known as photons, which demonstrate wave-like behavior unless observed, a phenomenon termed wave-particle duality. This concept is inherently paradoxical. These waves encompass various frequencies and are categorized into 7 primary sections based on their wavelengths, from expansive radio waves to minuscule gamma rays. Human vision is limited to a small segment of this spectrum, visible light, while the rest remains imperceptible. The significance of this range lies in the evolutionary development of eyes in underwater environments, where visible light efficiently penetrates water, unlike infrared and ultraviolet rays, which render water somewhat opaque. Were organisms to evolve in sulfurous lakes orbiting neutron stars, their visual systems might have adapted to perceive phenomena akin to X-rays. With this understanding, how does light form, and how does it contribute to our perception of color? Within the Sun's core, hydrogen nuclei undergo nuclear fusion under immense pressure, generating alpha particles and emitting gamma radiation. This radiation traverses the Sun, interacting with hydrogen atoms over millennia, gradually losing energy until it manifests as visible or ultraviolet light upon reaching Earth. When light encounters a surface, it can either be absorbed or reflected, contingent upon the material's composition. For instance, a blue fabric appears blue because it reflects blue light while absorbing other hues. Conversely, black objects absorb light, leading to heat accumulation, whereas white surfaces reflect most light, remaining relatively cool. This interplay between light and matter is termed bulk reflection and absorption. When light illuminates a collection of atoms, factors such as atomic spacing and arrangement influence the colors of reflected light. For instance, although snow and ice share molecular composition, their distinct arrangements result in divergent appearances, with snow appearing white and ice translucent. Water, possessing minimal light absorption, permits light to penetrate deeply, necessitating considerable depth to evade sunlight. Let's explore whether atoms exhibit colors in the context of bulk reflection. Simply put, atoms do not possess discernible colors at this scale due to the vastly larger wavelengths of light compared to the size of individual atoms, rendering color perception impossible. However, when a substance is heated, its constituent atoms become more energetic, resulting in the emission of photons, a phenomenon known as thermal radiation. It's intriguing that heating any substance elicits a spectrum of colors, yet this phenomenon is only observable when numerous particles are present together. Isolated atoms do not emit noticeable colors when heated. Now, let's delve into the phenomenon of gas discharge, wherein passing electric current through a group of atoms excites them, causing the release of photons. The emitted light varies in color depending on the specific substance involved, thereby generating a distinctive color pattern for each element. For instance, hydrogen atoms emit characteristic colors, as do elements like iron. In essence, each element possesses its unique emission spectrum, which we might perceive as the element's color in our daily experiences. However, it's crucial to recognize that atoms are minuscule compared to the wavelengths of light. Thus, the conventional notion of color does not directly apply at the atomic level. Now, let's address another question: why don't protons within atomic nuclei repel each other? In nature, 4 primary forces govern interactions: gravity, the weak force, electromagnetism, and the strong force. While gravity is more familiar in everyday contexts, on the atomic scale, electromagnetism, the weak force, and the strong force predominate. Electromagnetism, approximately 10 to the power of 37 times stronger than gravity, is responsible for attracting electrons to protons within atoms. You may wonder why protons within atomic nuclei, subject to electromagnetic repulsion, do not forcefully repel each other. According to Coulomb's law, in a helium atom, 2 protons should experience significant repulsion, driving them apart instantaneously. However, they remain bound together due to the influence of a much more potent force known as the strong nuclear force. This force, approximately 100 times stronger than electromagnetism, operates within atomic nuclei, effectively counteracting electromagnetic repulsion. Despite its dissimilar mode of action compared to electromagnetism, the strong nuclear force is the primary factor ensuring the cohesion of protons within the nucleus. Although less commonly discussed outside of advanced academic settings, The realm of quantum chromodynamics elucidates the mechanisms by which protons and neutrons remain tightly bound within atomic nuclei despite the formidable electromagnetic repulsion they encounter. The strong nuclear force, which binds atomic nuclei, contributes approximately 99% of the mass of everyday matter, a fact that may surprise many, given the prevalent misconception regarding the role of the Higgs field. To grasp the strong force better, let's delve into the composition of protons and neutrons. These subatomic particles are comprised of even tinier entities called quarks, which form the building blocks of matter, along with particles called gluons that mediate the force between quarks. Protons consist of 2 up quarks and 1 down quark, while neutrons contain 2 down quarks and 1 up quark. Gluons, akin to glue in the subatomic realm, maintain the proximity of quarks within particles. These gluons possess what's called a color charge, although it's not related to colors as we perceive them. Gluons come in 3 varieties, red, green, and blue, and when combined, they yield the neutral hue of white. To ensure electrical neutrality, all 3 colors must be blended together, or alternatively, color-anticolor charges can be employed. The interaction between gluons and quarks is pivotal for keeping them bound together. It's crucial to understand that the strong force predominantly influences quarks and gluons, acting as carriers similar to photons in electromagnetism. When quarks attempt to separate, it's akin to stretching a rubber band. Instead of allowing the quark to break free, the requisite energy generates a new pair of particles called a meson, comprising a quark and an antiquark. This principle dictates that free quarks cannot exist in isolation, they're always tethered to at least one other quark. Mesons play a significant role in the interactions between protons and neutrons within atomic nuclei. Although the strong nuclear force is weaker than the force operating within protons and neutrons, it far surpasses the repulsion resulting from the positively charged protons due to electromagnetism. An intriguing aspect of the strong nuclear force is its effective range, which is exceedingly short, approximately the size of a proton. Moreover, its potency diminishes rapidly with distance, thereby imposing a constraint on the maximum size of stable atomic nuclei. To gain deeper insights into its functioning, the strong nuclear force, aided by mesons, securely binds protons and neutrons within atomic nuclei. This force collaborates with the strong force, which binds quarks within protons and neutrons. A comprehensive understanding of the strong force is indispensable for comprehending the nature of matter and elucidating the reasons underlying the existence of various phenomena, including ourselves. Now, let's explore the dimensions of a proton, a diminutive particle at the core of the subatomic realm. Despite extensive research into atomic properties, a groundbreaking experiment in 2010 challenged our understanding of proton size, providing a new measurement that contradicted previous beliefs. Following nearly a decade of meticulous scrutiny, scientists believe they've resolved this enigma, often referred to as the proton radius mystery. First, let's dispel some misconceptions regarding atoms. Contrary to popular belief, a proton isn't akin to a smooth billiard ball, rather, it resembles a cloud of quarks held together by gluons, adding intricacy to our comprehension of its structure. Quarks play a pivotal role in shaping the proton's characteristics, particularly its positive charge. Therefore, understanding the extent of the region containing this positive charge aids in determining the proton's size. Over the years, scientists have employed 2 primary methods to ascertain the size of a proton. One method involves directing electrons at atoms, often focusing on hydrogen due to its simplicity, featuring a solitary electron orbiting a lone proton in the nucleus. Scientists meticulously observe the interactions between electrons and the nucleus to pinpoint where the proton's positive charge diminishes, indicating its boundary. The second method entails examining the energy required to transition an electron within an atom from one energy level to another. Hydrogen is often utilized for this purpose because its electron isn't solely confined to circling the proton in a low energy state. At times, it penetrates the proton itself. The interaction between the negatively charged electron and the positively charged proton influences their mutual attraction, thereby affecting the energy required for the electron to transition to a higher energy level. So, let's explore why the size of a proton matters and how scientists have sought to measure it over time. Initially, researchers used electrons to gauge the size, estimating it to be around 0.876 femtometers. However, a shift occurred about a decade ago when scientists turned to muons, which are similar to electrons but much heavier, about 207 times more. Due to their increased mass, muons spend more time within the proton, providing a clearer perspective on its size. In a notable experiment involving muonic hydrogen, scientists discovered that the proton size was approximately 4% smaller than previously believed based on electron experiments. This unexpected finding prompted a re-evaluation of past conclusions and sparked curiosity about potential new physics or undiscovered particles. Exploring the proton dimensions has become an exciting journey, challenging and expanding our comprehension of the fundamental constituents of the universe. In September 2019, researchers at York University in Toronto conducted a study using conventional electronic hydrogen, employing an advanced technique called frequency offset separated oscillatory fields. They measured the proton size by elevating the electron to a higher energy level. Remarkably, their findings aligned with those from the muonic hydrogen experiment conducted in 2010, with a proton radius estimated at around 0.833 femtometers. The convergence of results from diverse methodologies provides a clearer understanding of the proton size. This suggests that discrepancies observed earlier were likely attributable to measurement errors rather than indicative of novel discoveries in particle physics. Despite the apparent emptiness within atoms, they possess solidity, prompting questions about why objects cannot pass through this apparent void and why light cannot traverse the tiny gaps between atoms. To comprehend this, let's examine the behavior of electrons within atoms. The conventional notion of electrons orbiting like planets around the Sun oversimplifies their behavior. Instead, envision electrons as a dynamic swarm moving predictably, akin to birds or bees within an atom. Electrons resemble dancers in a synchronized performance. Although tracking individual electrons proves challenging due to their rapid motion, collectively, they form patterns akin to dance steps, guided by mathematical equations. These patterns can vary from graceful to frenetic, analogous to different dance styles. Governed by the exclusion principle, each electron follows its distinct pattern, never repeating the same steps simultaneously. Viewing electrons as dancers aids in understanding the organized chaos within atoms, elucidating why everyday objects possess solidity. While electrons do not tire, altering their dance patterns demands energy. Acceleration necessitates energy input, while deceleration results in energy release, often manifesting as light. When light interacts with electrons, these tiny particles absorb some of its energy, causing them to move to higher energy levels. This absorption process slows down the light, making it more difficult for it to pass through materials such as a table. Eventually, the electrons release the extra energy they absorbed, sometimes as light again. This exchange between absorbed and released light, coupled with alterations in electron movements, gives rise to reflections and colors. Altogether, this mechanism creates the perception of solidity in objects like a table. This prompts an intriguing question: if light doesn't penetrate deeply into the table, why does it feel solid when touched? The sensation of solidity when touching an object such as a table is linked to how electrons interact within atoms. As you reach out and touch the table, the electrons in your fingers come close to those in the atoms of the table. As they approach, their movements change because one electron cannot occupy the same space around the nucleus as another electron. Consequently, the approaching electron must jump to a higher energy level, requiring energy. Unlike when light is absorbed, this energy comes from the pressure exerted by your finger against the table. Pushing two atoms close together demands energy because all their electrons must transition to higher energy levels. Attempting to push all the atoms in your finger into those in the table necessitates a substantial amount of energy, surpassing what your muscles can easily provide. The resistance felt when pressing against the table arises from this energy requirement, elucidating why the table feels solid upon touch. Now, let's consider why atoms join together to form molecules. Despite the vast array of atoms, fewer than 100 different types compose the world around us. The myriad substances observed in both space and living organisms arise from atoms' inclination to bond with one another. This bonding capability engenders a diverse array of chemical compounds and materials, essential not only for the myriad phenomena in the world but also for the formation of complex structures crucial for life, energy sources, and even cognitive processes. In essence, the universe's vibrancy stems from atoms' propensity to combine and create new substances with distinct properties, governed by the principles of quantum mechanics at the microscopic level. Consider the air we breathe. Rather than individual atoms floating in isolation, they frequently unite to form molecules. For instance, oxygen typically exists as O2, comprising two oxygen atoms bound together, while nitrogen manifests as N2, and water adopts the form H2O, consisting of two hydrogen atoms and one oxygen atom. Atoms exhibit a tendency to form molecules because they seek a state of minimal energy, akin to a ball rolling downhill, a natural occurrence observed throughout nature, such as the flow of rivers downhill. Energy plays a pivotal role in shaping these molecular structures, particularly in the case of hydrogen, the simplest atom, which typically manifests as H2 or hydrogen gas. Quantum mechanics provides insights into why atoms collaborate to form molecules, aiming to achieve lower energy states. When a second hydrogen atom enters the picture, intriguing dynamics unfold. As the atoms approach each other, their negatively charged electrons repel one another due to their identical charges. Simultaneously, they are attracted to the positively charged protons in the neighboring atom. This delicate interplay results in the protons settling at an optimal distance from each other, enabling electron sharing while minimizing repulsion. It's essential to recognize that atomic attraction isn't solely dictated by electron cloud repulsion. Numerous intricate interactions influence molecular formation. Fundamentally, the movement of electrons and the interplay of charges at the quantum level facilitate atom-to-atom bonding, with each atom striving to achieve equilibrium in its energy state. The intricate process of atoms coalescing into molecules is governed by the principle of total energy within a system. This overarching energy determines how atoms bond, giving rise to cohesive molecular structures. Understanding this process in a two-atom system, such as when hydrogen atoms combine to form a molecule, necessitates consideration of various factors. The kinetic energy of each atom, coupled with the potential energy interactions between their protons and electrons, collectively contribute to the system's total energy. In the realm of quantum mechanics, the Hamiltonian serves as a tool for evaluating a system's energy. To decipher this energy puzzle, we grapple with a complex equation known as the time-independent Schrödinger equation, with the Hamiltonian providing guidance. While solving this equation directly can prove challenging, graphical representations aid in visualizing energy changes and understanding the intricate energy dynamics at play. In the provided graphs, we observe a dip as two atoms draw closer, indicating the system's lowest energy point. When these atoms reach an optimal distance, they establish a harmonious relationship, becoming more stable with lower energy compared to their solitary states. This phenomenon sheds light on why hydrogen atoms prefer to form H2 molecules rather than existing independently. Atoms engage in a unique connection known as a covalent bond when they share electrons, promoting stability. This bonding propensity extends beyond two atoms, offering insights into the mechanisms that maintain atomic stability. Examination of electron orbital arrangements reveals that atoms achieve maximum stability when possessing specific electron counts, 2, 10, 18, 36, 54, or 86. These figures correspond to the electron configurations of noble gases, which exhibit minimal inclination to bond with other atoms. Atoms strive for stability by endeavoring to fill their outer electron shells, achieved through electron sharing in covalent bonds or electron transfer in ionic bonds. However, this pursuit of stability is intricate, balancing the attractive force pulling electrons together with the repulsive force between electron clouds and the atom's nucleus. An understanding of the stabilizing role of specific electron counts unveils a narrative rooted in quantum mechanics. The Schrödinger equation and the Pauli exclusion principle play pivotal roles in elucidating this phenomenon. The Pauli exclusion principle dictates that no two electrons can occupy the same quantum state, necessitating opposite spins if they inhabit the same orbital. Integration of these principles reveals distinct numerical patterns, termed magic numbers, governing the lowest energy configurations in chemical systems. Comprehending intricate systems involving multiple atoms, such as water, H2O, demands meticulous calculations. The Morse potential equation serves as a valuable tool, aiding in determining the optimal bond length for molecules to attain the lowest energy state. Quantum mechanics, with its comprehensive rules and mathematical framework, facilitates our comprehension of natural phenomena. However, it's essential to recognize that while quantum mechanics offers insights into the behavior of matter, it does not invariably elucidate the reasons behind their existence. Now, let's explore a captivating subject: neutron stars. Are they akin to colossal atoms? Neutron stars exhibit unparalleled characteristics in the cosmos, boasting sizes spanning kilometers and possessing incredibly dense and turbulent cores. This prompts a compelling question: how can entities like neutron stars exist? The life cycle of a star hinges on a delicate equilibrium between gravitational collapse and outward pressure from radiation. Within a star's core, hydrogen atoms undergo fusion, transforming into helium. Over time, as stars progress, they deplete their hydrogen reserves, leading to helium fusion and the subsequent synthesis of heavier elements like carbon. During stellar evolution, the core accumulates layers of progressively heavier atomic nuclei. Fusion reactions convert carbon into neon, then oxygen and silicon, ultimately forming iron, marking the cessation of fusion processes. When fusion halts, radiation pressure undergoes a sudden decline, disturbing the star's equilibrium. If the core exceeds approximately 1.4 times the mass of the Sun, it experiences catastrophic collapse. Outer core layers hurtle inward at velocities up to 70,000 km per second. At this critical juncture, only the fundamental forces within an atom can withstand the collapse. However, in the intense, compact environment, protons can readily convert into neutrons and vice versa due to the influence of the weak force. As the universe's temperature gradually drops, approximately 1 second after its inception, the weak force begins to diminish, causing a slowdown in the conversion between protons and neutrons. This period, known as freeze-out, marks the settling of particles like protons and neutrons into their distinct identities. It's a crucial juncture where fundamental constants of nature, such as the masses of quarks, start to influence the universe's future trajectory. Neutrons, consisting of 2 heavier down quarks and 1 lighter up quark, possess slightly more mass than protons, composed of 2 lighter up quarks and 1 heavier down quark. As the universe continues to cool, there's a pivotal shift in particle identities. Due to their heavier nature, neutrons preferentially transform into lighter protons due to lower energy requirements. This subtle difference in mass leads to an abundance of protons compared to neutrons in the universe, with approximately 7 protons for every neutron. This ratio plays a crucial role in shaping the universe's evolution. Protons serve as the fundamental constituents of hydrogen and helium, the primary fuels for stars and the foundational elements for all other elements. Their positive charge enables interactions with other particles, laying the groundwork for chemistry and the emergence of life. Had certain fundamental properties, like the mass of the down quark, been different, the universe's composition and development would have been drastically altered. A scenario where neutrons are lighter would result in their outnumbering protons, imposing constraints on the range of possible chemical reactions. Hydrogen, consisting solely of a proton, would exhibit unstable behavior over time. While some protons might persist by binding to neutrons before decaying into helium atoms, helium's inherent stability would hinder easy reactivity, especially in the presence of numerous neutrons. In such a universe, sustaining nuclear fusion, the process fueling stars, would prove challenging. The outcome would be a cold, desolate cosmos, devoid of stars, galaxies, planets, or life as we know it. Hence, the prevailing preference for protons over neutrons in the universe, albeit not fully comprehended, is a fortuitous circumstance. Another significant divergence that influences the universe's evolution is the absence of antimatter. Envision gazing up at the sky one day and witnessing an alien civilization annihilating itself, an event as potent as a stellar explosion, signaling the existence of a catastrophic weapon capable of obliterating entire worlds. Throughout Earth's history, conflicts and disputes have been commonplace among civilizations, suggesting that other planets might confront similar challenges. On a planet akin to Earth but characterized by heightened hostility, the quest for dominance triggers an arms race, spanning from conventional weaponry to cutting-edge technologies such as nanomachinery and atomic bombs. These advanced extraterrestrial beings harness antimatter as a weapon. They master the production and containment of antimatter particles, harnessing electromagnetic forces to confine them until deployment. Unlike conventional armaments, antimatter weaponry requires minimal fuel or intricate mechanisms. When antimatter particles encounter regular matter on their planet's surface, they undergo annihilation, unleashing immense energy and self-destructing in the process. Even a minuscule quantity of antimatter, such as a gram, can unleash energy equivalent to that produced by a traditional nuclear bomb utilizing approximately 90 kilograms of fuel. Some theorists have put forward the intriguing notion that our universe might be akin to an atom within a vastly larger cosmos. One such concept, the one-electron universe theory, proposes that what we perceive as numerous electrons could, in fact, be a solitary electron traversing time at incredible speeds, creating the illusion of multiplicity. While this theory lacks robust scientific support, its contemplation has spurred the development of similar hypotheses. Another compelling concept is the multiverse theory, positing that every constituent of matter in our universe, atoms, electrons, and their characteristics, might mirror atoms within a broader cosmic framework. This idea prompts us to envision the existence of myriad other universes, each governed by its distinct rules and attributes. It's akin to regarding our universe as a mere fraction of a grander cosmic puzzle. These theoretical frameworks prompt profound inquiries into the scale and expanse of the universe, inviting speculation about the existence of even grander realities beyond our perception. Within these frameworks, the notion of infinity assumes a prominent role, suggesting the possibility of universes infinitely larger than our own. From the vantage point of these expansive realms, our universe could appear as diminutive as atoms do to us. As we delve into the vast expanses of the universe, we are confronted with the prospect of something even more expansive lying beyond. This prompts contemplation regarding the potential existence of a comprehensive explanation that reconciles everything from the minutest particles to the grandest galaxies. Scientists are diligently pursuing a grand unifying framework known as the theory of everything, which seeks to harmonize the principles of quantum physics governing the microscopic realm with classical physics describing phenomena on a macroscopic scale. According to prevailing scientific understanding, the universe originated from a minuscule, extraordinarily dense entity termed a singularity. Subsequently, it underwent rapid expansion in an event known as the Big Bang, culminating in the formation of the diverse cosmos we inhabit today. However, it's crucial not to equate this singularity with a conventional atom, as it harbored the fundamental constituents necessary for the eventual emergence of atoms. Although these concepts may challenge conventional wisdom, their contemplation is essential for elucidating our place within the broader cosmic framework. String theory has emerged as a prominent contender in the quest for the theory of everything. It posits that, rather than resembling discrete particles, atoms might fundamentally comprise vibrating strings. These strings purportedly underpin all phenomena in the universe, from gravitational forces to particle interactions. Nonetheless, string theory confronts several enigmatic facets, particularly regarding the comprehension of dark energy, a mysterious force that constitutes a significant portion of the universe. Numerous string theory models grapple with elucidating the abundance of dark energy compared to observable matter. In a bid to unravel this conundrum, researchers at Uppsala University in Sweden have proposed a novel conjecture within string theory. They postulate that our universe might constitute a minuscule bubble within a broader cosmic construct that undergoes perpetual expansion. According to this perspective, undiscovered dimensions may exist, and dark energy from the larger universe outside our bubble may infiltrate, driving the observed expansion. If this idea proves to be correct, it would revolutionize our perception of the universe. It suggests that humans are minuscule components of a vastly larger and more intricate system than previously envisioned. However, it's crucial to acknowledge that this remains a theory, a framework for scientists to ponder significant questions. Even though we might appear insignificant from this standpoint, it doesn't diminish the importance or meaning of our lives. Now, let's contemplate a timeless quandary: what happens to your atoms when you pass away? Throughout history, millions of individuals have lived and died. According to the law of conservation of matter, which asserts that matter cannot be created or destroyed, one may wonder about the fate of all those atoms. Do they persist in some form after death? Let's delve into a fascinating concept: the notion that the atoms from deceased individuals endure and play a role in shaping the world around us, embarking on an ongoing journey through the cosmos. By exploring this idea, we can uncover the intriguing mechanisms behind this transformation. The human body comprises various substances, with water being predominant. Upon death, the water in the body undergoes transformation. It either evaporates into the atmosphere or infiltrates the ground. The pace of this process is influenced by factors such as temperature and environmental conditions. Even if the water remains in liquid form, it eventually becomes part of Earth's water cycle, transitioning into vapor, ascending to the clouds, and precipitating back to the ground as rain. A substantial portion of this rainwater finds its way into rivers, lakes, and eventually becomes the water we consume. This water serves numerous purposes in your body, including cell formation, temperature regulation, and vital bodily functions. Some rainwater is absorbed by plants, essential for photosynthesis, a process wherein plants utilize water, carbon dioxide, and sunlight to produce carbohydrates and oxygen. The oxygen emitted by plants is indispensable for sustaining life, while the carbohydrates from photosynthesis become part of our diet through the consumption of fruits and vegetables. This cycle exemplifies how the atoms of deceased individuals persist in the cycle of life, connecting all living organisms and illustrating the fluidity of atoms across various forms and functions. As we examine how atoms and molecules traverse the body, let's delve into metabolism. When you ingest carbohydrates from plants, a crucial process occurs: the generation of substances vital for plant survival, such as carbon dioxide and water. This initiates a cycle wherein the elements you generate support plant growth and vitality. Now, let's consider the fate of the tissues in your body, composed of carbohydrates, fats, and proteins. These tissues undergo metabolism facilitated by approximately 100 trillion bacteria inhabiting your body, primarily in your gut, which have been with you since birth. Typically, your immune system regulates these bacteria. Upon death, the immune system ceases to function, allowing bacteria to commence tissue breakdown. This metabolic process, akin to a slow combustion, sees bacteria utilizing tissues for energy and replication. The molecules in these tissues transform into water and carbon dioxide, analogous to combustion outcomes. Additionally, proteins in the body emit gases like nitrogen oxides and ammonia, potent greenhouse gases that trap heat in the atmosphere and contribute to global warming. Even posthumously, the elements in our bodies continue to participate in environmental processes. Even after death, bacteria continue their activity within the body. Initially, they consume oxygen, paving the way for anaerobic bacteria to thrive. Unlike their oxygen-dependent counterparts, these bacteria can function in the absence of oxygen. As they decompose tissues, they generate malodorous byproducts such as methane, hydrogen sulfide, and ammonia. Apart from their unpleasant smell, these byproducts are potent greenhouse gases. Over time, these gases escape from the body and disperse into the atmosphere. Therefore, when you detect unusual odors outdoors, you could be inhaling atoms derived from deceased individuals. Moreover, as your body decomposes, additional atoms and molecules are released into the soil beneath. For every kilogram of dry body mass, approximately 32 grams of nitrogen, 10 grams of phosphorus, 4 grams of potassium, and 1 gram of magnesium eventually contribute to the soil. Surprisingly, these components act as natural fertilizers for plants surrounding the burial site, benefiting the local ecosystem. Now, let's consider the alternative process of cremation. During cremation, the intense heat converts the majority of atoms in your body, hydrogen, carbon, nitrogen, oxygen, and sulfur, into gases. This transformation marks a significant change in the state of these atoms, representing another chapter in the intricate journey of elements within the cosmic cycle. After cremation, various gases, including water vapor, carbon dioxide, nitrogen oxides, and sulfur oxides, are released into the atmosphere. Additionally, a considerable portion of your remains, amounting to several kilograms, transforms into ash. Interestingly, the weight of these ashes is roughly equivalent to your birth weight, highlighting the cyclical nature of life. Analyzing the composition of these ashes reveals that the bulk consists of phosphate and calcium. This composition aligns with the integral role these elements play in the structure of bones, primarily originating from your skeletal framework. These ashes are likely to integrate into the soil, becoming part of plant structures. Consequently, these plants may serve as a source of nourishment for animals and humans, contributing to the cycle of life. In a fascinating twist, small fragments of you could end up in the morning cereal or burger of your great-grandchildren, perpetuating your contribution to sustaining life on our planet. However, it's essential to note a significant exception: your body contains trace amounts of radioactive elements. Some of these elements undergo spontaneous fission through radioactive decay, transforming into other elements before entering the biosphere. For instance, radioactive potassium may transition into calcium, while minute quantities of thorium and uranium within your body will eventually evolve into lead. Alongside this decay process, certain helium atoms are generated. Due to the insufficient gravitational force on our planet, helium tends to escape into space, although a fraction may be captured by massive celestial bodies like the Sun and Jupiter. This intricate interplay of elements adds complexity to the cosmic journey of atoms that will end it off right there. Thank you so much for watching this documentary. Be sure to like this video and subscribe. Until next time.